In this next section, we're going to be looking at probability distribution. So we're going to start by looking at a few key definitions to make sure that we are happy with some of the terminology. So a random variable is a quantity whose value depends on chance. This is a phrase that you're going to hear repeated a lot, and just to give you some examples, we've got 4 here. X is the number of sixes obtained when a dice is rolled 3 times. B is the number of babies in a pregnancy. M is the mass of crisps in a packet, and T is the time taken for a runner to complete 100 meters. Now, just to refamiliarize yourself with some of the key ideas, there are 2 basic types of random variables. So what I want you to do is just classify those 4 examples into 2 groups. Hopefully that should be fairly easy to identify what those 2 groups are. Just have a moment to try that. So the first group is discrete random variables. Now these are variables which have a finite or a countable number of possible values. So you can see the number of sixes obtained is going to be finite. It's going to be an integer value, as with the number of babies, whereas in M and T they are going to be continuous random variables. The time taken for a runner to complete 100 meters is going to be given to the nearest split second, or some finite level of accuracy, even though that is only an estimate. As with M, the mass of crisps in a packet, that's going to be given to a specific degree of accuracy. A probability distribution then, in the case of a discrete random variable, is a list of each possible value of the random variable and the probability that each outcome occurs. So that's quite a mouthful. So let's try and have a look again at an example to make sure we get the gist of that. Suppose x then is the random variable. We could use any letter here, but we're going to use x to be the random variable that represents the number of sixes obtained when a fair dice is rolled 3 times. So again, as a review exercise of your understanding of probabilities so far, what I want you to try and do is tabulate the probability distribution for x. So try and find the probability of rolling the dice 3 times and getting no sixes, 1 6, 2 6, or 3 6s. Okay. Hopefully you would have started off by drawing a tree diagram. So you can see up here we've got the probability of getting a 6, so we're assuming it's a fair dice. And we're going to roll the dice 3 times. So I could have got a 6 on the first go, 6 on the second, and a 6 on the third time. That's the only way I could get 3 6s. The probability there, multiplying along the branches, is going to be 1 over 216. There are going to be a number of different ways you can get 2 6s. So I could have 6 6 not 6, or I could have 6 not 6 6, etc., or not 6 6 6. Similarly, there are going to be a few ways I could get 1 6. And then here, no 6s is going to be 5 of 6 multiplied by 5 of 6 multiplied by 5 of 6. So if we look at all these different probabilities, we can represent them in a table, which is essentially our probability distribution for this function. So x, the number of 6s being 0, so the probability that if we roll our dice 3 times we get no 6s is going to be 125 over 216. There's only one possibility. The probability of rolling the dice 3 times and getting 1 6, well, you can see there's going to be 3 ways we can do that. If we add those together, we get 25 over 72. It's for rolling the dice 3 times and getting 2 6s. That's going to be adding together these 3 probabilities to give you 5 over 72, and again only one way we can get 3 6s, which is this one up here. And that is it. That is our probability distribution for this example. We should remember that if we've done it correctly, all of these probabilities will add up to 1, and indeed that is true not only in this instance but for any random variable x. The probability, the sum of the probabilities will add up to 1, and each individual probability should be somewhere between 0 and 1 inclusive. Let's have a look at a different probability distribution here then. So we've got the probability that a random variable x takes the value of 1, 2, 3, 4, and 5. And we've got the probability. So it is 7 times some constant c. Find the value of c. And then once you've done that, use that to find the probability that x is greater than or equal to 4. So again, just pause the video and have a few minutes to try that by yourself, and then you can work it through with me. So the first thing we're going to do then is recognize that the sum of all these individual probabilities will add up to 1. So if we just add these together, we'll get 20c equals 1. So we can find the value of c, which equals 20. To find the probability that x is greater than or equal to 4, so that means we're talking about this value or this value. So we are going to add those two probabilities together. We know what c is, so we can add those together to get a value of 1/5. The next key concept is the mean, or more often referred to as the expected value. So we're going to be looking at the expected value of a random variable x, which is the average value that we would expect for this random variable over many trials of the experiment. And obviously the more times we do the trial, the more accurate this expected value, or more reliable this expected value is going to be. The terminology that we use to represent expected value is E brackets capital X. So how do we find it? The expected value, EX, is the sum of the individual probabilities multiplied by the possible outcomes. So in the context of this example that we looked at, what is the expected value for X, which was the number of times that you roll a dice and get a 6. So the expected probability is going to be the sum of the individual outcomes multiplied by their probabilities. So for instance, in the first one, we are going to multiply the outcome here, which is getting 0 outcomes, multiplied by the probability that x equals 0, which is going to be this probability here. So we're going to multiply these two together. Remember here it's the sum of the outcomes multiplied by the probability. So we're going to, once we've done this, we're going to then multiply this outcome 1 by the probability of achieving it, this outcome 2 multiplied by the probability of achieving it, this outcome 3 by the probability of achieving it, and we're going to add those together to get our expected value, which is going to be in half. Again, check it. Is it within the range? Yes, it is. So that is plausible. On a graphic display calculator on the TI Inspire, you can do this a little bit more quickly as well. Just enter, open up a new data sheet, put in the two titles of X and P. So X, remember, represents the individual outcomes, P is the probability. Once you've done that, you can go to, this is the one variable statistics tab, and if you look at the results here, you'll find that the expected value can be taken from the mean. So remember, we introduced this as the mean or the expected value. Typically we refer to it as the expected value, but if you're going to find it on your GDC, you can find it under the mean here, using X as the X1 list on a calculator and P as the frequency list.